There we go. There we go. Just wait for people to get here, and then I'll start recording. This is going to be some tasty food. Let's get some lemonade. Okay, so we got one person here, so let's do it. Okay, so today's stream is going to be all about how to calculate the resistance from Firth's principle. So that's to say, starting with the microscopic form of Ohm's law and then defining the current in terms of the current density, we're able to find what the resistance of some system is by using those two pieces, as well as the definition of the difference in electric potential. So just to lay out those three equations, they're going to be things that we're going to be using throughout. So the first one is the microscopic form of Ohm's law, which just says that E is equal to rho times J. Where we remember from class that here rho is not the charge density, it's the resistivity. And J is the current density. The current density can be related to the current by saying that the current is just equal to the flux of the current density. So I did want to talk a little bit more about this because I had some questions after class that made me realize that I probably could have explained this better. So what the current density is it's the amount of charge that's flowing per area. So the current just tells you that there is some charge per time. So current, the units of current are just charge per time. And we see that the current is a scalar quantity. The current density, which is a vector quantity, has units of charge per time times area in the denominator. And so what the current density really tells us is, one, it tells you some direction, right, because it's a vector. And it also tells you what the concentration of charge is that's flowing. So for instance, if I had a whole bunch of charges here and they're all going to be flowing in this direction, we could relate the current density that I have here to some other current density where I have a whole bunch of charges all bunched up. And now these ones are flowing. This has a larger amount of charge in smaller areas. So this would be a larger charge density than this one. Okay. So the last thing that, that we need in order to work these kinds of problems, we have the microscopic form of Ohm's law. We have the definition of the current density in terms of the current. We just need our old friend, the definition of the difference in electric potential. So that's to say that some difference in electric potential between, let's say, two arbitrary points, R1 and R2, is going to be equal to the negative integral from R1 to R2 of E dot dl. And there is kind of one more thing that we can write here, and that's the macroscopic form of Ohm's law. So we're going to use these three pieces to go to this piece, ultimately. Okay. So in order to show this, what I'm going to do is a couple of the examples that we did from class today. And the first one was to consider some cylinder that has this hole cut out of the middle. So this is going to be some distance A, some distance B, and this is some constant resistivity, rho naught. And this was a two-part question. So the first part was to find what the resistance is if the current is going to flow from left to right. And then the second part was to find what the resistance is if instead of having it flow left to right, it's going to flow radially outward. So to consider the first part, what we can do is we have our microscopic form of Ohm's law here. What we want to do is we want to write this in terms of just the current. So in order to do that, what we can do is we can look at this flux of the current density, integral of J dot dA, and write this in terms of the cross-sectional area that this current density is flowing through. So just like Gauss's law, we can reduce this because the current density and the dA vector. So the dA vector, if I was going to draw one of these cross sections that this is going to go through, dA is going to be pointing to the right in this case, and also the current density is pointing to the right. So that allows me to say that this is just the integral of J times dA. Now the other thing is the current density is not going to vary over the same variables as dA. And so I can pull that outside of the integral, and so this is just J integral dA. And we've seen plenty of these integrals of this form this semester. This is just going to be J times A. Okay. So now the question is, what is the area that this current density flows through? And it's just going to be equal to pi times the outer radius squared minus the inner radius squared. So this is J pi b squared minus a squared. Okay, which is equal to I. So we can write J in terms of I by saying that J is just going to be equal to I divided by pi b squared minus a squared. And then we can plug this into our microscopic form of Ohm's law. So this says that E vector is just going to be equal to rho I divided by pi b squared minus a squared in the x hat direction, because we're saying that this is going to be pointing to the right. Okay? So the next thing that we can do, and this is almost the last step now, actually, is just to find what the difference in electric potential between here and here is. In the problem, I said that this is some distance L. And so what we can do is we can say delta V is going to be equal to the negative integral from 0 to L of E dot dl. Now you have to be a little bit careful with the notation here, because I said that this is some distance L, and I have this dl, but dl vector here is really just going to be x hat dx. Because what I'm saying is that this direction is the x direction. All of the little pieces of electric field that I'm adding up are going to be these little dx's. So what this says is this is going to be equal to the negative integral from 0 to L of rho I divided by pi b squared minus a squared x hat dot x hat dx. We see that this integrand is going to be just some constant. And so when we do this integral, we end up seeing that this is just going to be equal to negative rho L divided by pi b squared minus a squared times I. Okay? So now what we can do, we found what delta V is. If we want to take some magnitude of delta V, that's just going to make this plus. And then we can compare it to the macroscopic form of Ohm's law. So that's just to say that V is going to be equal to I times the resistance. And so this term right here is just the resistance that we have. So R is going to be equal to rho L divided by pi b squared minus a squared. And that's it. Okay. So the next question that I asked here was to find what the resistance is if instead of having the current flow from left to right, I have the current flowing from the inner surface to the outer surface. So the current's going to flow like this. We can get rid of these ones. So what this is going to change is actually this portion. It's also going to change what our limits of integration are. I'll get to that in a moment. But what it's going to change is what the area that the current density is flowing through. And the way that we can see that is we have the current going radially outward like this, there's some surface very similar to a Gaussian surface that we can draw that parameterizes what the area that this flows through. So there's going to be some infinitesimal area that's around the outside of this, this shell of area that has some variable radius of r. And so what that does in effect is we can come down to here and we see that I is just going to be equal to j times a, where now instead of a being the cross-sectional area that we have, this is just going to be the area of the cylinder that we have here. And so this is just going to be j times 2 pi r times L. Okay? So now we can rearrange this again, and what we see is that our current density, J, is just going to be equal to I divided by 2 pi r times L. And again, we're just going to go through the same process. So now that we have what the current density is, we can plug that into our microscopic form of Ohm's law. This says that E vector is going to be equal to, this is going to be rho times I divided by 2 pi r L, pointing out in the radial direction now. And now the last step that we're going to have is just to calculate what the change in, or the difference in electric potential is between this inner surface and this outer surface. So this is going to be equal to the negative integral from A to B of rho I divided by 2 pi r L times r hat dot, in this case, dl vector is going to be r hat dr. And we can see the reason why this should be a dr is because really what I'm doing here is I'm adding up all of the electric field, taking this walk from this inner radius to the outer radius. And the direction that that is going is going to be the r hat direction, and the little pieces are little pieces of dr. Okay. So this is going to be r hat dot r hat dr. This is an integral that we can evaluate pretty easily. And so this part's just going to give me a 1 when I do the dot product. All of this stuff except for the r in the denominator is a constant. And so what I'm left with is this is going to be minus rho I divided by 2 pi L times the integral from A to B of dr over r. This is just going to give us a natural log, and so this is going to be equal to minus rho I over 2 pi L times the natural log of B minus the natural log of A. Okay. Now we can use some rules for combining natural logs, and so ln B minus ln A is really just ln B over A. Okay. And then we can ask ourselves, is this answer positive or negative? If we plot the natural log is 0 at 1, okay? And for any value greater than 1, it's going to be positive. Any value less than 1, it's going to be negative. We know that B is greater than A, and so whatever this ratio is going to be strictly larger than 1. So this is actually already positive. And so when I take this absolute value, that's just going to get rid of this, negative sign that I have here. Okay. Now, to compare this to the macroscopic form of Ohm's law, I can bring my I out over here so it's really suggestive of what the resistance is. I have my I. Everything else is going to be my R. And so what that says in this case is R is going to be equal to rho divided by 2 pi L times the natural log of B divided by A. And that's our answer. Okay. I'll pause here and see if anybody has any questions about this before I move on. Like I said, the process, same thing with Gauss's law really, the process is always the same. It's just a matter of the geometry that you have and how do I parameterize these areas, and ultimately then how do I write my limits of integration. Okay, so we could, and this is really what your homework's going to be, so I'm not going to explicitly do this, but we could have, we did this with cylindrical symmetry, we could have also done this with the spherical symmetry. And just to give you an idea of how that works, imagine I have spherical shells now. So I have, this is just going to be some resistivity rho. Again, we want to be able to write the current in terms of the current density, and so we know that I is equal to the integral of j dot dA. Now in this case, if I say that the current is going to flow radially out of the center of this sphere, this is just going to say then that this integral of j dot dA is going to reduce to j times a, which is going to be j times 4 pi r squared. Okay. Now that's the real important thing here, and then we just need to figure out how to evaluate the integral as we go through this process, and then what our limits of integration are in the case that say this is A and this is B. Okay. The second problem that I had you guys do here in class today was really trying to get at the idea of how do I add resistors in series. After this question, you can always just use the equation that tells you how to add resistors in series. But really what I was trying to get at in asking this question is, what is that equation? And so the problem that I had set up here had some, I don't know why lately I've had a hard time drawing these rectangular prisms. But this is just some rectangular prism that is in contact with some cylinder, where this has some resistivity of rho 1, this has some resistivity of rho 2. Let me just make sure I'm doing it exactly the same. So that's rho 1, rho 2. This is going to be W and H. This is some capital L. This is some lowercase l. And then this has some radius of A. And so this was kind of multiple steps that took you in two different directions that I wanted. Ultimately, what I wanted to show here was that resistors add in series like this. So the equivalent resistance is just going to be equal to the sum of the individual resistors. So the first thing that I asked was to find what the difference in electric potential was between this end and this end. So this is finding what delta V is. And so in order to do that, what we needed to do was to find what the electric field here was and what the electric field here was. So let's first look at E1. So E1 is going to be equal to rho 1 times J1. And so the current I, which is actually the same current in both of these, right? Because the charge per second that moves through this has to be the same, because there's not going to be some accumulation of charge, and there's not going to be a loss of charge. All of the charge that comes in has to be the charge that's coming out. So this I, like I said, is going to be common to the two, but this can be written for J1 as J1 dot dA1. And so the same way that we reduced this before, this is just going to be J1 times A1, where this is just going to be J1 times H times W, right? Because that's going to be the cross-sectional area of this guy, okay? Now we can plug this into our electric field. E1 is going to be equal to rho 1 times I divided by H times W, okay? So now we have what our first electric field is. So this is the first electric field. The second electric field follows exactly the same process. So E vector 2 is going to be equal to rho 2 J2. I is going to be equal to the integral of J2 dot dA2. And so this one is just going to be J2 times pi A squared, right? Because that's just going to be the cross-sectional area of this guy, okay? So from this, what we can say is E vector 2 is just going to be equal to rho 2 times I divided by pi A squared x hat, okay? Almost there. We just need to find what the difference in electric potential is between these two ends. And so in order to do that, we say that delta V is going to be equal to the negative integral of E vector dot dl from 0 to L plus capital L, right? Because it starts here and we want to define what the difference in electric potential is between the two ends. Now, in order to evaluate this integral, what we need to realize, and something that we already did realize, is the fact that we have two different electric fields in these two regions. And so when we want to do this integral, what we need to do is we need to say this is equal to the negative integral from 0 to L of E1 dot dl minus the integral from L, capital L, to capital L plus lowercase l of E2 dot dl. Okay? So we can plug in our electric fields, and when we evaluate what these integrals are, we're going to end up seeing that this is just going to be equal to minus, this is going to be minus rho 1L divided by HW times I, minus rho 2 times, this is going to be L plus L, capital L plus lowercase l minus capital L, so we're just left with a lowercase l, divided by pi a squared times I is equal to delta V. Okay? So we can take an absolute value of this, and so that's just going to make this plus plus, and we can factor out our I. And so this is just the total resistance of the whole thing. So let's write that down over here, and then we'll continue. So this is just to say that our total is just going to be equal to rho 1L divided by HW plus rho 2L divided by pi a squared. Okay? So that was just the first part, to do this just in terms of finding what the difference in electric potential is between this end and this end. Okay. Oh, I froze. I froze. Hopefully that wasn't like that very long. How do I fix things? Okay. Okay. That should be good. Okay. Yep. I'm back. So I just did the from where we left off. I just wrote what the total resistance was over here because I want to look back at that a little bit later. And so now the next part says, so that was actually part 1 and 2. Part 3 asks us to find what the difference in electric potential is across each one of these resistors individually. Okay. So if we do this individually, what we can do is we can actually, I'm going to keep my electric fields because the electric fields are going to be the same. This is just to say that delta V1 is equal to the negative integral from 0 to L of E1 dot dl, and delta V2 is going to be equal to the negative integral from 0 to lowercase l of E2 dot dl. Okay? So when we take these electric fields and then plug them into these integrals, what we end up seeing is that delta V1 is just going to be equal to negative rho 1I divided by HW, and delta V2, there should be a capital L here. Delta V2 is just going to be equal to negative, this is going to be rho 2I times lowercase l divided by pi a squared. Now, the next thing that I wanted you to see was, well, really, delta V total is just equal to delta V1 plus delta V2. And so I can take these two things and then just add them together. And actually, I'm going to take my absolute values now too. So you take an absolute value of all of these things. What I end up seeing is this is going to be rho 1 divided by HW L times I plus rho 2 lowercase l divided by pi a squared times I. I can see that I can factor out an I here. And what we see is that by doing these individually, we get the same answer. And what that tells us then is when we have these resistors in series, we can actually just write what the total resistance is by saying that the total resistance, or total, or sometimes it's written as REQ, the equivalent resistance, is just equal to the linear sum of R1 and R2. Okay? Because that's literally what we did right here. Okay? So that was the takeaway from this problem. Now in the future, same thing with when we did the capacitors. I wanted you guys to go through the process of showing why it is I can say that this REQ is equal to R1 plus R2. From now on, whenever you have one of these types of problems, you can just say the total resistance when two resistors are in series is just equal to the sum of the two resistances. Okay? Pause here for any questions. And actually, I don't really have anything else to say unless if there's some particular questions that you guys would like me to answer. That'll probably be it. Okay, any questions? Going once. Going twice. Going 2.5 times. Okay, well if there aren't any questions, then that's going to be it for this one. I think having gone through Gauss's law and capacitors, as long as you're careful with the way that you're defining the geometries here, these are actually not very difficult problems. I think that you know, there's only really so many ways that I can write a test question, and the things that I can change or vary with these. So if you practice with all of the symmetries for these, which really shouldn't take you more than like 2 hours in studying for the exam. So between now and the exam, if you spend like 2 hours doing these resistance calculations, you've really covered just about everything that I can ask. Okay, so that's going to be it. I'll see you guys in class tomorrow.